So here I'm trying to look at a problem in multiple different ways to show you how you can use your labels, the definitions that we know, and the units that we have to get to an answer. So we've got a sample, or we've got a sample of iron oxide. That is its formula in this case, iron 3 oxide. It's almost 70% iron by mass. And we have not quite 60 grams of iron. So obviously our compound is heavier than that, but how much heavier? One way we could apply this is by thinking about what the percent means. Well, if 100 grams or if 69.94 grams out of every 100 is iron, then 100 grams is the whole compound. Boom, boom, we do this. We could also think about, well, if I have 58.7 grams of iron, well, the two irons in it would be 55.85 times 2. The whole compound, so I'm using my molar mass, would be 59.69 grams. So the mass of just the iron in the compound versus the mass of the whole compound. That gives me about 84 grams as well. We'll note that these are the same ratios, but in slightly different proportions, getting them from different ways. Or we got iron here. Well, there's 2 irons in every iron oxide. There is this much iron in every iron oxide. Our units don't match up quite as cleanly here. And why did I do that? I have probably in the wrong order here, but we still get to the same answer. What would be the best way to do this? Doom, doom. These would probably want to be in the... I don't know. Sorry. But it is true. There is 2 of these in every one of those. So basically taking this and splitting this into a part. I apologize to myself for that. But you could also think about this. Well, if I have this much iron, how much oxygen would I have? Maybe you'd want to write the reaction and you'd have a 3-to-2 ratio of that. And then you'd add those together. There's lots of ways to do this. Maybe you would write the formula and do the ratio of iron to iron oxide, which is actually where I got that from. Sorry for my own confusion, but I put it all in one step. So whatever makes sense, if you can label it and if you can make sense of it with those labels, that's great. On B, determine the mass of oxygen in this sample of aluminum sulfate. So what I did was kind of the same skills as up here. The mass of the whole aluminum sulfate, I needed that in both cases. It was 342.15. That's just adding up 2 aluminums, 3 sulfurs, and 12 oxygens. Well, there are 12 oxygens in it. I show that here. I show that there as well. Each oxygen is 16. So here I've broken it out to show my process. Here I did it all at once, the 192 grams out of this. You could also find a percent and then deal with it as a percent. But either way, we've got 7 grams and a little bit more than half of that is coming from the oxygen. So in terms of a free response, we could find that. Beware, and we'll practice this in class and in videos on the multiple choice. You should also be able to kind of ballpark or estimate this. If you see there's 12 oxygens there, wow, that's a lot of mass. So it makes sense that over half of the mass does come from the oxygen. This last one is what we would, not last one, sorry, this next one is what we would call like the combustion analysis of a hydrocarbon. We have a compound made of just hydrogen and carbon. It's reacting completely to make water and CO2. The STP is important. We will review that coming up, but maybe that makes you think of the number 22.4. So what I'm thinking about here is the empirical formula. Well, I'm not told how many carbons I have. I'm not told how many hydrogens I have, but I am told at the end I have a compound that's got hydrogen in it. At the end, I have a compound that has carbon in it. So what I want to do is, if I have that much water, and that's the only place the carbon could go, that means all the hydrogen that's in the water came from my original compound. So then I change this. Well, how many grams of hydrogen is it? There's 2 grams for every 18 grams of water. Well, I have that much hydrogen. That means I have this many moles of hydrogen. So I've found a way, kind of using those empirical formula skills. If I need to know my grams of an element, well, how many grams of hydrogen are in this? Boom, 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 boom. I've got that. And then grams to moles. Well, how many how many moles of CO2? Because this is in liters. I may not want to go to grams, but I want to go to moles. Well, I've got this, boom, boom, boom. Every mole of CO2 is 22.4 liters. I have that many moles of CO2. Well, every CO2 has one C in it. So when I'm thinking empirical formula, I need to recognize, I need to know the moles of carbon and the moles of hydrogen. Well, I get moles of hydrogen by thinking about the fact that water is the only thing with hydrogen in it. I get moles of carbon by thinking the carbon dioxide is the only thing with carbon in it. I divide by the smallest, as I've done. It comes out to 1 to 2.5 as the ratio. That divided by that is 2.5. I can't use those subscripts. The times 2 is what gets me my C2H5. So this is kind of a huge leap forward and different than even A and B on this, but it goes back to empirical formula. I need to know the moles and mole ratio of my two compounds. What data relates to the amounts of those, the water and the CO2? And then the next few here, we've got a lot here because we want to see a lot of different skills. Maybe some of the other videos you haven't had to watch, but this one's good because it's new and different. A compound, potassium, bromine, oxygen with some substrate is analyzed and over half of it's bromine. So is this BRO1, 2, 3, or 4? So if we thought about we had a 100-gram sample, which we do in empirical formulas, that means we have 52.92 grams of bromine. That allows me to know how many moles I have. The formula shows me there's 1 K for every 1 Br. From given formula, the moles of bromine equals the moles of K. So that means it's 1 to 1, or I have this much K. Then I'm kind of going back the other way. This is one where you have to think about, problem solve, determine what you can do next in lots of different ways. But that tells me I have 25.9 grams of K in this imaginary 100-gram sample. 100 grams, well, 52 grams of it are bromine based upon the percent. 25 grams of it are potassium based upon the mole-to-mole ratio and the molar mass, which means that in that 100-gram sample, there would be 21 grams of oxygen. Well, 21 grams is 1.32 moles. I already know how many moles of bromine. I already know how many moles of potassium, bromine, and then I just found my moles of oxygen divided right there. So when we want to find a formula, we need moles of everything. But we need to think about how we can take percents to grams to moles, how moles of certain things do relate to moles of other things. You could have maybe just done some guess and check on this, and that would have been fine. Well, what if it's a 1? Is that 53% bromine? No. What if it's a 2? Is that 53% bromine? Yes, it is. What if it's a 3? What if it's a 4? Those are good methods as long as you're showing your work, showing your logic, and coming to the right conclusion. And then the last one here is about something called a hydrate. So you just bought some new shoes, you open up, you get the paper off, and there's that little packet in there, silica gel, do not eat. Hydrates are ionic compounds that absorb water. That little packet is absorbing all of the moisture and the humidity so your shoes don't get funky before you ever open them up. Another example of that is called washing soda. It's sodium carbonate with a certain amount of water molecules bonded or trapped inside. If we had a sample of that, almost 3 grams of the hydrated version, the sodium, carbon, oxygen with some waters, and we heated it up, that ionic compound has a really high melting point. It doesn't melt, but the water boils at 100. So those waters go away and become humidity, water vapor, etc. So then we only have 1 gram or so of the ionic compound left. We're then asked, well, how much water was stuck inside? I am thinking about formulas. It has to be in terms of moles. So the 1 gram of sodium carbonate tells me how many moles. But then the problem is that 2.74, that's the mass of that whole compound. I don't know its formula. It's a mixture. I can't find the molar mass of something if there's an X in the middle of it. So I have to think about it another way. The 2.74 was the solid with the water. The 1 was the solid without the water. Subtracting those is the amount of water. So I have the amount of water that I know the chemical formula, therefore the molar mass, so I can find the moles. I take the moles of water, the bigger number of moles, divided by the moles of the smaller number of moles. I'm looking at an empirical formula or a mole to mole ratio. It's a 1 to 10 ratio, or every single one of those sodium carbonates can trap 10 moles of water in it. So on all of these, the keys when we're thinking about formulas, how can I get it to moles? What do the different numbers mean and how do they connect to one another? And lots of different ways. If I'm asked about an individual compound, how can I use molar masses, or how can I use percents, or how can I maybe even write a chemical reaction that helps me to understand it? So don't be afraid to be creative, but keep your work organized. If you don't get to the right answer, cross it out. Don't waste your time erasing it and start fresh, showing what you know the right answers are.